An electronic circuit is made up of various components. These can be classified into passive elements and active elements. Let's begin by taking a look at passive elements. Most substances exhibit what is known as electrical resistance. Resistors are elements within a circuit that take advantage of the characteristics of electrical resistance. Resistors are used to control electric current and to convert current signals to voltage signals. Resistors come in various shapes, sizes, and materials, depending on their use. Furthermore, some are fixed resistors with a fixed value of resistance, while others are variable resistors whose resistance value can be altered. Fixed resistors are denoted on the electrical circuit like this, and variable resistors are expressed like this. Some resistors are color-coded to indicate their resistance value. Color codes can be used to calculate resistance value. Now let us explain how to read color codes. A numerical value is assigned beforehand to each color. Color codes can be printed for any terminal. The fourth color band indicates resistance error. The value of resistance can be determined by applying color code values to a prescribed formula. This carbon film resistor, for example, has yellow, purple, red, and gold color bands, arranged in order from left to right. Their corresponding values are 4, 7, 2, and 5. From these numbers, we can determine that the resistance value is 4.7 kiloohms and the error is plus or minus 5%. The illustration here is an electrical circuit comprising a battery, switch, and resistor. This circuit can be shown with a circuit diagram like this. When the switch is turned on, voltage E is applied to resistor R and current I flows. This relationship is known as Ohm's law. For example, if voltage E is 100 volts and resistor R is 100 ohms, the current I is 1 amp. If you wish to control the current to 0.5 amps, then R should be 200 ohms. Controlling the current is one of the functions of the resistor. We can also deduce that voltage of 100 volts is generated between the resistor terminals when a current of 1 amp is passed through a resistor of 100 ohms. For example, resistance of 100 ohms will be used to convert current of 0.1 amps into 100 volts. Heat is generated when current flows through the resistor. This means that the resistor consumes electric power. The formula P equals E times I is derived when the voltage of the resistance is considered as E, current as I, and electric power as P. If Ohm's law is substituted here, we obtain the formula P equals I squared times R, or P equals E squared over R. Thus, as electric current increases, power consumption increases. As a result, the resistor's temperature rises due to heat generation. This means that the resistor will burn if the current is too strong. As such, each resistor has a value for maximum allowable electric power. When resistors with high power consumption are cooled for, products that can control heat generation by means of forced air cooling or water cooling may be used. A capacitor is an element used to temporarily store the electric charge. Capacitors are used for a variety of applications. Even a small electronic device like a mobile phone uses nearly 100 capacitors. Among the uses of capacitors are Temporary storage of electrical energy. AC and DC separation and selection. Phase shift between voltage and current. And signal differentiation and integration. While external appearance and structure may vary from capacitor to capacitor, the basic structure can be represented by a pair of electrodes. When voltage is applied between these electrodes, the electric charge accumulates on the surface of the electrodes. The larger the surface area of the electrodes, the larger the amount of electric charge that can be stored. The narrower the distance between the electrodes, the larger the amount of electric charge that can be stored. The amount of storable electric charge can be increased by inserting an insulator, known as a dielectric, between the electrodes. The characteristics of capacitors differ according to the type of dielectric used, making it possible to employ capacitors for a variety of applications. Some capacitors have no polarity. Others do have polarity. The capacitors shown here are in common use. They represent a small proportion of all capacitors. Regardless of polarity, capacitors are indicated like this in electrical circuit diagrams. An exception is the electrolytic capacitor, which is indicated like this to differentiate it from the other capacitors. When voltage E is applied between the terminals of a capacitor, a proportional electric charge Q is stored in the capacitor. The proportion coefficient C is known as electrostatic capacitance. The following formula is obtained. Q, electric charge, equals C, electrostatic capacitance, times E, voltage. Aluminium electrolytic capacitors offer high capacitance at a low price, leading to their frequent use for applications wherein the voltage of the electrical circuit board must be kept constant. Compared to other capacitors, however, they have a relatively short useful life, about 7 to 8 years on average. This does not mean that they cannot be used after 7 or 8 years. It means that electronic devices that use aluminium electrolytic capacitors may begin to generate heat or emit noise as they age. Using the aluminium electrolytic capacitor in a cool environment lengthens its useful life. Research indicates that useful life can be doubled by reducing the ambient temperature by 10 degrees Celsius and trebled by a reduction of 20 degrees. On any electronic circuit board, numerous aluminium electrolytic capacitors are used. The lifespan of these electronic circuit boards is generally determined by the lifespan of the aluminium electrolytic capacitors. A spare electronic circuit board is provided on board ships in case the board in use breaks. This spare electronic circuit board must be placed in a cool place to ensure that it can be used over an extended period of time. However, the electronic circuit board may become rusty if this cool place is humid. To prevent rusting, an electronic circuit board can be stored in a plastic bag, along with a dehumidifying agent. An inductor is a circuit component comprising a coil of conductive material wound around a core. Inductors temporarily store magnetic energy. Although capacitors are more common, several inductors can usually be found on an electronic circuit board. Functions of the inductor include temporary storage of energy, AC and DC separation and selection, phase shift between voltage and current, and magnetic field generation. While inductors vary in terms of external appearance and construction, the fundamental design is that of a core with a conducting wire wound around it. Inductors are classified by shape, of which there are two types, solenoid and pancake. Inductors used on electronic circuit boards are mostly of the solenoid coil type. A greater amount of magnetic energy can be stored when the solenoid coil is wrapped around a ferromagnetic core. The core itself can take a variety of shapes, depending on the application and voltage current. The larger the current that passes through the coil, the more magnetic energy is stored in the inductor. This characteristic varies depending on the number of loops in the coil, the shape of the core, and so on. The functional characteristic of the inductor is known as inductance and is expressed in units of H, Henry. Some electrical equipment generates electrical noise, known as noise. If precision equipment like a temperature measuring device is electrically connected to electrical equipment generating noise, it may not function properly. To avoid this problem, an inductor may be used as a noise filter. Compared to resistors and capacitors, inductors are less susceptible to damage. When they are damaged, it is often difficult to detect from external appearance alone. Insulation film applied to the coil will deteriorate in environments with high ambient temperatures. In the worst case, the coil short-circuits and is no longer capable of functioning as an inductor. Coils are found in the motors of seawater and freshwater pumps, and their insulation is weakened by the absorption of moisture. The main purpose of measuring insulation resistance using a mega is to check for coil insulation degradation. The transformer has a structure featuring two or more coils sharing one core. Magnetic energy generated in one coil is transmitted to the other coil through the core. The main functions of the transformer are to increase or decrease AC voltage and AC current, and to insulate multiple electrical circuits. Let's look at the transformer turns ratio, using as our example a transformer with a toroidal core. If we take the number of primary turns as N1, that of secondary turns as N2, input voltage applied to primary turns as E1, and the output voltage of secondary turns as E2, then we have this formula. And we can rewrite it like this. And if we take the current in the primary turns as I1, and that in the secondary turns as I2, we have this formula. And we can rewrite it like this. Please note that the transformer can handle AC voltage and AC current only, and that it cannot convert DC voltage and DC current. Let's now look at the voltage used for lights on board a ship. When the generator voltage is 440 volts, a voltage of 110 volts for inboard lights can be obtained by setting the ratio of primary turns to secondary turns as 4:1. The number of large-size ships offering generator voltage of 6,600 volts has been growing. A transformer turns ratio of 30:1 is employed to convert this voltage to 220 volts, which is compatible with the engine room pump. Devices that make use of semiconductors are all around us and include cellular phones, personal computers, and CD players. A variety of electronic equipment making use of semiconductor parts can also be found on board and include control panels in the control room and nautical instruments on the bridge. Let's take a look at the basics of semiconductor devices. Copper, aluminium, stainless steel, and iron exhibit low electrical resistance and therefore are effective conductors of electric current. Hence, they are known as conductors. On the other hand, the electrical resistance exhibited by glass or ceramic materials is extremely high. Such materials are known as insulators. Semiconductors have intermediate properties. Semiconductor devices have functions similar to those of a water tap. The resistance that water encounters decreases when the tap is opened, allowing a lot of water to flow out. As the tap is gradually closed, increased resistance makes it difficult for water to flow out, resulting in reduced water flow. When the tap is closed completely, resistance is at its greatest, and the flow of water stops. In semiconductor devices, the electrical signal is substituted for water, and the semiconductor functions as both a conductor and an insulator, i.e., as the tap. In short, the semiconductor device can control the flow of current. This function makes it possible to process electrical signals and convert electric power. Because of its properties, control over the semiconductor device can be lost, resulting in malfunction or breakdown. It also generates heat during use. A heat sink and fan are used to prevent the semiconductor device from overheating. To ensure the maintenance of a low ambient temperature for semiconductors, it is important to periodically check that the fan is working properly and that the panel intake filter is not blocked with dust and oil residue. Also referred to as a rectifier, the diode is a semiconductor device that works as a check valve for electrical circuits. Check valves are used in pipelines to prevent water, steam or fuel from flowing backwards and ensure that the liquid flows in one direction only. Similarly, diodes ensure that electric current flows in one direction only. A positive or negative signal is acquired using this function of the diode. It also converts alternating current into direct current. There are various types of diode. Let's look at some typical diodes. This one converts single-phase AC voltage, or three-phase AC voltage, into DC current. It is comprised of 4 or 6 diodes and has a synthetic resin cover. This is another type of diode. It is used when a high-speed operation such as DC power supply or inverter functionality is needed. Among other types of diode are the Zener diode and LED. Its advantages are low power consumption and long life. In terms of structure, transistors can be classified into 2 types, the PNP and NPN. The transistor is a semiconductor device with 3 terminals, the collector, base, and emitter. The transistor is a semiconductor device that functions like a water tap. When the amount of current IB passed to the base is altered, the flow of current between the collector and emitter also changes. This results in a change to the current IC of the collector. It becomes possible to control the large collector current IC by the small base current IB when the voltage between the collector and emitter is high. This function of the transistor is known as the amplification effect. A microphone is one example of a device that uses the amplification functionality of a transistor. Without the transistor, the sound produced by a microphone connected to a speaker is small because the electrical signal from the microphone is small. However, by adding a transistor, the electrical signal can be amplified before reaching the speaker, yielding a louder output. A thyristor is a semiconductor device that can handle a large amount of electric power. This means it is possible to use thyristors for high-voltage electrical circuits with large currents. Today, thyristors for high-voltage circuits of 12 kilovolts are available on the market. Moreover, thyristors that can handle currents as large as 5,000 amps are also available. The thyristor is also known as a semiconductor switching device. Unlike mechanical switches, thyristors have no moving parts, and thereby enjoy a long, useful life. Another feature is their fast switching speed. When pulse current is passed through the gate, the thyristor turns on. The on state is maintained once the thyristor is turned on. The current flows in the forward direction like a diode during the on state, but current does not flow in the reverse direction. To turn it off, it is necessary to reduce the current to zero, there are various ways of doing this, or by applying reverse voltage to the thyristor. Thyristors are chosen according to type of ship and application for which they will be used. Shaft power generators are widely used as devices that generate power by extracting partial power from the output shaft of the main diesel engine or steam turbines. In this shaft generating system, the frequency of the generating voltage remains unstable because the number of output shaft rotations varies according to ship speed. Thyristor inverters are used in shaft power generators to resolve this problem. When it comes to semiconductor products, including thyristors, it is important to guard against static electricity. Static electricity has a small amount of current, but the voltage can be several kilovolts or more. People are usually unaware that they have picked up electricity, making it possible for several kilovolts of static electricity to accumulate before they know it. Touching a semiconductor device in this state can cause the device to break down, a situation that can go unnoticed, since visibly it does not appear to have changed. To prevent electrostatic destruction, it is necessary to remove static electricity from the body prior to handling a semiconductor device or electronic circuit board. It is easy to rid yourself of static electricity. One simple method is to touch a tap with your bare hand. When on board ship, you can touch the steel deck, floor, or ship side for several seconds with your bare hand. However, touching an FRP wall surface or glass can actually build up static electricity. Insulated gate bipolar transistors, or IGBTs, come in various shapes and sizes depending upon the application or voltage. An IGBT is a semiconductor switching device similar to the thyristor. IGBTs turn on or off when signal voltage is input at the gate terminal. IGBTs enable a switching speed faster than that of thyristors and operate in a range from several to 10 kHz. Widely used in inverters for motor control, IGBTs are indispensable to controlling a motor's rotational speed and torque. IGBT inverter-controlled motors are often found in anchor winches and mooring winches. A metal oxide semiconductor field effect transistor, or MOSFET, is a semiconductor switching device like the IGBT. Due to a fast switching speed, MOSFETs play a vital role in enhancing the performance of power devices. For example, electronic circuit boards for communications equipment and control devices operate with a stable DC voltage. MOSFETs ensure the stable and efficient supply of DC voltage to these pieces of equipment. The mechanism by which a machine is operated step by step in accordance with prescribed procedures is known as sequence control. Many pieces of equipment operated automatically using sequence control can be found on board ships. As a simple example, there is a sequence circuit to automatically supply fuel oil to a settling tank by a fuel oil transfer pump. This sequence circuit controls the fuel oil transfer pump, stopping the pump before the fuel oil in the tank overflows, and resuming pump operation as the level of oil in the tank drops below a preset level. The motor that supplies power to the pump generates a modest amount of heat while operating. However, when the motor has been stopped, its temperature gradually begins to decrease. If the motor's temperature becomes cooler than the ambient temperature, condensation on the casing and coil could result. Condensation inside the motor can result in overcurrent, an event that takes place when insulation resistance between the coils decreases, leading to a short circuit. Reduced insulation resistance between the coil, motor, and the motor frame can also lead to electrical leakage. To prevent such accidents, an electric space heater can be installed in the motor. The space heater is off when the motor is running, and it turns on after the motor has been idle for a preset period of time. In the sequence diagram, the upper half is the main circuit supplying a three-phase electric supply of 440 volts to the motor, and the lower half is the sequence circuit controlling the power supply. Single-phase AC voltage of 110 volts is used in the sequence circuit, but in some cases, AC 440 volts or DC 12 volts is used if the location and conditions require this. The notation method is now being unified under IEC standard, but old JIS or JIS is still used. Now let's take a look at the variety of elements found in the sequence circuit. Switches and relays are classified according to operation. The three types of operation are make contact, break contact, and changeover contact. Make contact is also known as Arbeit contact, which is abbreviated as A contact or form A. If A contact is not in operation, the circuit remains open and the off state is maintained. The circuit remains closed and the on state is maintained only while A contact is in operation. Because of this, the indication NO, or normally open, will often appear on the A contact terminal. The A contact push button switch closes the circuit when the button is pressed and opens the circuit using spring force when the button is no longer being pressed. Break contact is also known as B contact or form B. If B contact is not in operation, the circuit remains closed and the on state is maintained. The circuit is closed and the off state is maintained only while B contact is in operation. Because of this, the indication NC, or normally closed, will often appear on the B contact terminal. The B contact push button switch opens the circuit when the button is pressed and closes the circuit using spring force when the button is no longer being pressed. Changeover contact is also known as C contact or form C. C contact combines the features of A contact and B contact. Prior to operation, A contact is off and B contact is on. When the switch is operated, A contact turns on and simultaneously B contact turns off. The A contactor closes and B contactor opens when the C contact push button switch is pressed, and they return to their original states when the button is no longer being pressed. Shown here is a turnover switch, a C contact with residual function. A control relay is composed of a spring, electromagnetic coil, a free-moving piece of iron, and a relay. When a current is passed in the control relay coil, the coil turns into an electromagnet and attracts the piece of iron. The relay is turned on or off by interlocking with the piece of iron. The electromagnetic power of the coil vanishes when the current passed through the coil drops to zero. Spring force returns the piece of iron to its original position. As you can see, many control relays are of the C contact or form C type. These are schematic symbols for the control relay. It is expressed as a circle in old JIS and as a rectangle in IEC standard. The number 4 indicates that the particular control relay is for use in the main control circuit. In an actual sequence circuit, the dotted line connecting the coil and relay is often omitted. The main contactor is used to turn on or off heavy load current supplied to the motor or heater. The main contactor's structure is similar to that of the control relay. It turns on when a current is passed through the built-in coil. An auxiliary relay similar to a small control relay is attached to it, and it is interlocked with the operation of the main contactor. In many cases, it is abbreviated as MC in the circuit diagram. The figure 88 is the control device number for the MC. For MCs used on ships, circuit diagrams are just as likely to be rendered in old GIS as in IEC. The relay may appear to be a capacitor at first glance, but the difference between the relay and the capacitor can be determined easily. Just look for the number 88. The timer relay is a kind of control relay. It can prolong the relay operation, but only for a set period of time. Most timer relays offer a choice of several operation modes. Chief among them are the on-delay mode and off-delay mode. In on-delay mode, the relay begins to operate when a set period of time has elapsed after current is passed through the coil. However, the moment the current passing through the coil becomes zero, the relay returns to its original state. In off-delay mode, the relay begins to operate the moment current starts flowing through the coil. However, when the current becomes zero, the relay returns to its original state once a set period of time has elapsed. The thermal relay is composed of a main circuit terminal with a built-in heater and bimetal and an auxiliary relay. It is used to intercept the circuit when the latter exceeds a certain limit. In the sequence circuit, it is possible to detect overcurrent using this auxiliary relay. The auxiliary relay will not return to its original state even if the excessive current is stopped. Therefore, it must be manually reset once the excessive current error has been resolved and safety has been confirmed. In these circuit diagrams, 51 and THR indicate thermal relays. In many cases, the thermal relay is incorporated in the MCCB and electromagnetic contactor. A variety of sensor switches are used in the sequence circuit. With sensor switches, the relay operates when the temperature, pressure, or water level reaches a preset value. A pressure switch is composed of components that detect pressure and an auxiliary relay. The relay operates when pressure rises above or falls below a set value. It is used for controlling air compressors and air conditioning compressors. With the level switch, the auxiliary relay operates when the water level in the tank rises above or falls below a certain level. There are various methods for detecting water level. In the float-type level switch, for example, the relay is operated by the vertical movement of the float. Since a limit switch is used for the relay, the level switch is often represented using the same symbol as for the limit switch in the diagram. An electrode-type level switch is also used. When multiple electrodes of varied lengths are inserted in the tank, the water level in the tank can be determined by detecting the state of the current passing through each electrode. The upper and lower limits of a tank's water level are indicated by the electrode's locations. The temperature switch relay operates when the temperature rises above a preset value. Thermistor and bimetal are often used in the temperature detection component. In some temperature switches, the relay is operated by a special liquid enclosed in the sensor that expands due to heat. In many cases, the temperature switch is represented in the circuit diagram using the same symbol as for the limit switch. Now let's look at the various devices that can be found in this sequence circuit. The molded case circuit breaker, or MCCB, is often referred to as the non-fuse breaker, NFB, or simply the breaker. The MCCB intercepts the circuit when current exceeding the rated